The typical reactions that alkenes and alkynes are going to go through are going to be addition reactions. So whatever I react with gets added to my original molecule on each end of the alkene or the alkyne. Now, however, the alkyne is kind of interesting because since at the end of the reaction there's still an alkene left oftentimes, it can sometimes react again to do two addition reactions. That's going to be a common thing that we're going to see with the alkyne reactions. So let's take an example and look at exactly how this works. So I'll just use ethylene and react that with HBr. So our standard question is always there. Who has electrons and who wants them? So we have HBr, which is an H plus Br minus. So H plus wants electrons. And the way that alkenes always react, at least alkenes that are by themselves and not conjugated to something else, the way they always react is they have electrons. So there's extra electron density here. And if you think about it, this bond is weak, it's easy to break, which means that these electrons are fairly reactive and ready to go somewhere. So we've got who has electrons and who wants them. Now all we have to do is draw an arrow, break the bond between H and Br, add an H to one side of my alkene. I chose to add my new H here. And the other side of the alkene, because I added a proton to it, has a positive charge. This side lost an electron. Since there's a positive charge there, and I have a bromide now in solution with a negative charge, the negative bromide is attracted to the positive charge on the carbocation. And here's what we've added to our alkene. You can draw the other hydrogens in, just so you can see them. But the new piece that we added was right there. So that's our addition reaction of adding HBr to an alkene. So if you want to draw a reaction coordinate diagram for this reaction, you could. So there's definitely an intermediate here in the middle. So it has to be a stepwise reaction. And this product is going to be lower energy than the starting material, at least lower energy than the alkene, because I've replaced one pi bond with two sigma bonds. Now in the process I had to break one sigma bond for HBr. That's a fairly weak bond in the first place, because remember how much those want to separate. So if I'm going to draw this then, it needs to be stepwise, somewhat favoring products. Here's my energy on that axis, and here's my reaction progress. Here's my intermediate, which is the carbocation. Once again, the first activation energy should be the highest, because again, we're going from two neutral molecules to charged species. So we're going up to somewhere that's higher energy in the middle, where we have charge, and then we go over a smaller energy barrier at the end to get to our product. To mix two charged things together, the carbocation and the bromide ion. So that's all fine, but what if our molecule is not symmetrical? Now we have to try to decide where our proton is going to go and where our chloride is going to go. So let's take a reaction and we'll draw both possible ways that it can go. So I'll draw two versions of the same reaction, and we'll try and decide which one's going to be better. So the mechanism is going to be the same. It's always going to be the same. The electrons start at the electron pair from the pi bond and go out and grab a proton. This bond breaks to chloride, giving us a carbocation. Now the choice is, where do we put the hydrogen and where do we put the carbocation? So one choice is to put the hydrogen here and the carbocation at the end. The other choice is to put the hydrogen here and the carbocation in the middle. Pause the video for a second and think about this problem, and you decide which one's going to be lower energy. This is a primary carbocation, or this one's a secondary carbocation. So the secondary carbocation is going to be lower energy, or more stable. Intermediate. So if I want to think about my reaction coordinate diagrams again, if I have a lower energy intermediate, then I'm probably also going to have a lower activation energy for that reaction. So here's my more stable intermediate. And this is actually based on Hammond's postulate. It means I've got a lower activation energy. So it's more likely to form. So I'll form more of this intermediate. Now if I carry the reaction through and take my Cl- and add that back in, my chloride comes in and attacks the carbocation to form my product. And the product that I'm going to get is the more substituted product. That's what Markovnikov's rule is. So the more substituted product is favored due to carbocation stability.